Okay, good afternoon, everyone. Welcome again to APNIC eLearning web class. Today is Wednesday, the 8th of April in 2015. It's already 3 p.m. in the afternoon from Brisbane in Australia, where I'm broadcasting this class. This is the third session, and the topic that we're going to cover is OSPF, Open Shortest Path First. So we'll just go through the basics of OSPF operations. Before we go on to the details, I'd like to also take a few minutes to introduce myself. My name is Cheryl Hermoso. I work for ePNIC. I'm part of the training team. And as part of the team, we conduct workshops, face-to-face trainings, sessions, e-learning classes like this on topics that are related to internet technologies. So network security, IPv6, DNS and DNSSEC, internet resource management, routing, and BGP. So this session is related to the routing curriculum. Now, a brief reminder that this class will run for 1 hour. The way to communicate with me is using the chat panel. Audio and video is not allowed coming from participants in the interest of bandwidth. At the end of the class, I will be asking you to fill in a short survey just so we can gauge this session and how it has appealed to you, and if you have any maybe suggestions for future courses. Okay, now that is out of the way. This is what we're going to cover for the class. An overview, a very brief one of what we're going to cover for the next 1 hour. First of all, this is about OSPF, right? So we'll go through some OSPF basics and features. OSPF is a type of link state routing protocol. So we will also try to understand link state routing to have a better understanding of how OSPF works. Okay, part of that, we will also look at some of the, okay, I'm just looking at why you can't hear me, what seems to be wrong. We're trying to adjust it now. Is it getting better? How's the audio now? Hello, can you hear me? Is that better? Okay, I think it's the best that we can do now. Can you, if you can put your volumes up, that will also be good. Sorry about that. So, okay, now that's out of the way, let's go through the overview. So as I've said, we'll look at link state routing protocol. We'll look at some of the characteristics of OSPF. So more specifically, let's try to understand convergence and how it works. We'll look at its operations, the different steps that are involved in it. We will look at OSPF neighbor discovery process, the different packet types and formats, and a typical, so I have some examples of some untypical OSPF network topology. So that's the idea. Hopefully, we will have enough time to cover everything. Okay, now let's understand what's OSPF. That's just a brief introduction of what it does. In order for us to understand that, it's also good to, of course, know what's routing. I'm assuming that coming into this class, you have an idea of routing. Routing, as you know, is the process of forwarding packets between different networks, between different nodes. It uses layer 3 device. You have either a router, or in the old days, we call it as a gateway. OSPF specifically is a type of routing protocol. It stands for Open Shortest Path First. This type of routing protocol is very popular nowadays. It's a type of link state routing protocol. So it uses link state, or more typically we call it as SPF, shortest path first technology. Now there are two types, or three general types generally of routing protocols. We have distance vector, which is a very old protocol. PRIP uses that. Now we also have link state routing protocol, which is OSPF is an example for. Now OSPF, we have two different versions. We have OSPF version 2, okay, and OSPF version 3. Now OSPF, I'm trying to use my pointer and it doesn't seem to be working just a little bit. Yep, you have OSPF version 2, which is a standard which is described in RFC 2328, and it is for IPv4. OSPF v3, on the other hand, is the IPv6 implementation implementation of OSPF, and it's described in RFC 2740. So you notice that you have two different versions, and for you to run both of IPv4 and IPv6, you have to have, or you have to implement both of them. Okay, now some of the characteristics of OSPF. OSPF is designed for IP networks. Okay, so we'll expound on that later on. OSPF also has fast convergence. One of the things that make OSPF a popular type of protocol is because of its fast convergence. Convergence is a timing unit. It determines how quickly OSPF or the protocol will be able to forward packets. So when you start the routing protocol in the router, it starts with learning the topology first. After it learns the topology, then it will build the routing table. Then only after that, after you've finished those two steps, that the router will start forwarding the packets. Okay, so then the convergence time basically refers to the point where it starts learning about this, okay, about the topology and all that, up to the point that it forwards the packet. In OSPF, this is done fast, really, really fast actually. If you are using variable length subnet masking in your network, okay, it can also just deal with that. It can route all those subnets. Now, older versions such as RIP version 2 and even RIP version 1, they work on classful boundaries. They don't work with VLSM. So with OSPF, that's kind of one difference between OSPF and some of the older routing protocols. OSPF does incremental updates. If there are changes in the network topology, only these changes or updates will be sent to the neighbor, not the entire topology. This is also one reason why convergence can be achieved fast. Another characteristic of OSPF, well, by the way, you can do route authentication, but OSPF also runs on protocol 18.9, so it's useful for IP protocols. If you see OSPF, the way it sends control information, it only works in IP. So there's that dependency in IP. It doesn't work with any other types of protocols. So for IPv4, as I've said, use OSPF v2. For IPv6, use OSPF v3. Now the next slide shows you a schematic diagram of a link state routing protocol. So the things that I will be explaining in here generally applies to OSPF. So we'll try to get a visual idea of what link state routing protocol is and how it works. So when you use link state routing, this is what happens. If you look at the diagram, we have about 4 routers there. And then each router is, you have Q, Y, Z, and X. And each of these routers have a number of links going to the different routers or to the other routers in the network. In all these routers, there are networks that are connected in the same fashion. So the networks that are connected to them are kind of in a different state than the others. They have their own topology in itself. And when we use link state routing protocol, each of these routers maintain a routing table. And each of these routing table will have their own, what we call as topology table or topology databases. Okay, that's because the network that's connected to them are unique to them, right? So they will have a mapping, I would say, or a table that maps the topology of those networks. So we have one OSPF instance. All these 4 routers will at some point share the same topology database. Okay, from this topology database, each of the routing protocol will now use algorithms. Specifically, it's the SPF algorithm. So we will use that algorithm to select how to get from point A to point B. What is the best way, or what is the shortest path to get from point A to point B? In such cases, each router will have, so this router here, Q, if it needs to go to one router connected to Z, may have a different best path compared to router X connected link going to one router or one host in network Z. So it's different. They all will share, as I said, the same topology database, topology table, but each of the router will then compute the best path all by themselves. They will have different values for that. Now notice that in the diagram from router Q, the best path is different from router Z or even from router Y for that matter. The topology table are identical. Routing table, okay, is going to be different. Okay, so bottom line, you'll have the same topology database, but calculating the best path will be different. SPF algorithm calculation is based on and dependent on your routers and how it sees the other networks. All right, so that's kind of what happens or what goes on when you talk about OSPF or generally with link state routing protocol. Now, some characteristics that are important or that are unique, I mean, with link state routing. Question from Ankit: how topology is formed for each router here? How can it become same topology? Well, let's go through that. That's why we're here. We will go through the details on how this is done step by step with OSPF. In that diagram, it's just a general overview of how link state routing works. And SPF, OSPF, being a type of link state routing, will basically do the same. Now, here are some of the characteristics of link state routing. First of all, it does not send the full routing table. It only sends a few of them, but it sends incremental updates only on periodic intervals. You will probably hear me saying this a lot over the next 1 hour. But this is one of the main characteristics, main features of link state routing and also OSPF. They do not send a full routing table. Okay. If you're familiar with distance vector routing, that's what it does. So this makes it different from distance vector. The disadvantage of sending the full routing table every time going to your neighbors, especially if you have heaps of neighbors, is that you get to influence your neighbor's routing table. Okay, this is what we sometimes call as routing by rumor. It is based on hearsay. I'm a router. I know the network. Okay, I have the topology database. I know how to get from point A to point B, but that is based on what I'm seeing. Now, if I send that routing table to you, the complete table, essentially I'm telling you what I'm seeing, and in that case, I'm influencing how I'd say how you will send to these networks. So you don't compute things yourself, right? It's based on hearsay. Again, it's called routing by rumor. In link state routing, we have established this through the example in the previous slide. That's simply not how the process works, right? We send incremental updates and then we then compute for the best path. Another is that link state routing maintains three types of tables. There is a neighbor table, so it contains a list of all my neighbors that I have OSPF links with. I have a topology table or a topology database which contains a routing information. Everything is there. It contains the optimal path, the best path. It also contains the second best path, the third best path, basically the suboptimal path. That's your topology table. But then we also have this last one, which is a routing table, which contains only the best or the optimal path. When the optimal path goes to the routing table from the topology database, the suboptimal path is still retained in the topology table. This is why, or this is how, OSPF can recompute best path straight away. If the best path maybe for for some reason goes down and becomes unavailable, the second best path contained in the topology table will now be passed on to the routing table. So at least you have there, it's a fast way or an easier way um, to get to the next best path, right? So it uses the shortest path first algorithm to select the best path. We'll go through those details again later on, and each router will use this. Next, it sends very small periodic um, hello messages to maintain link condition. All right, so in the neighbor table, you have the list of all your neighbors, right? Now, every so often, every intervals of time, your router will send hello messages to all the other neighbors just to check whether the link is still up. The periodic hello message going to its neighbors maintains the link condition. Okay, for example, you have two routers, R1 and R2, they're neighbors. They build their neighbor relationships, they build their routing table, they start sending and forwarding packets in between each other. This is the usual flow. At some point in time, the link between R1 and R2 goes down. How does each router know about this? Okay, there is this control signal, the hello messages we've said, that is sent at certain intervals between them that determines the neighbor status. The amount of time depends on the topology. Normally, for Ethernet links, it's about 10 seconds. So this is how your router can identify that the router link is down, if it's still up, by sending these periodic hello messages to maintain the link condition. Now, they also send triggered updates instantly when network changes occur. So you don't have to wait for that interval of time, that flow message. But if something happens, if suddenly the network goes down and the router is no longer participating in OSPF, or in the network there is a change, then your router can send trigger updates to the neighbors and let them know that this link has gone down. The neighbor router does not have to wait for the next hello update. They know right away that the link is already down. All right? So those are some of the characteristics basically of OSPF, right? If the neighbor will not respond, what will happen at certain point, it will stop linking with that. We'll go through some steps on how that's done. We'll see the different messages sent between the routers. Okay, so basically the steps on how they establish or build OSPF relationships. All right. Okay, we've already talked about these. These are the three different types of table. A neighbor table, which lists down all the recognized neighbor routers to whom we're exchanging or interchanging routing information. We have a topology table, which is also called the link state database. It maintains the list of all the routers, the link information, the best path, and the suboptimal path. And the last one is your routing table, which is sometimes also called as your forwarding table, which contains the best path, and this is used to actually forward the traffic. Okay, now let's understand about SPF. So we've been talking about shortest path first algorithm. So this one shows us the SPF tree. This is how SPF algorithms work. Every router shares the same topology table. Here is an example topology table, right? You can see that on here. So if we have this router X, router A, B, C, etc., they're sharing the same topology table. Now let's see how SPF tree path calculation works. When you look at the following diagram, assume that each path costs around 10. Okay, let's just use a fixed number, 10. Typically in real networks, in real setups, the links will have different path costs. Now let's say I need to go to one of the routers or one of the networks. Let's go to router F. Going there, what is the path from X going to F? I can take many different paths, right? So there are many paths to go there. X, A, D, F. So if this link, it can be X, D, F directly, can be X, C, D, F, can be X, C, E, D, G, F. So there are many paths going there. Now, if we look at this, since we're using the same fixed value for the cost, um, you will go for the lowest number of hops. In this case, XDF will have a path cost of 20, whereas XADF will have 30, XCDF is also 30, XCEGDF will have 50, right? So which one will you choose? Obviously, the one with the lowest cost. You notice that you can go through different paths. Each of them will have different costs, but each branch having a path cost associated with it will affect which path you will choose. Now, for example, in here, we said that your best path for this particular example is XDF because you only have 2 hops going to F, right? So that's only costing you 20 compared to the next one, which is XADF. But what if the path from X to D actually has higher cost? Maybe it's 50, okay? For some reason, different metrics will affect that bandwidth and all that. This path cost is 50. Therefore, your best path is now XADF. So that's essentially how shortest path first technology works. Each branch has a path cost associated with it. When they build the routing table, they add up the cost of each of the branch of the path, and among the many possible paths, they will try to calculate which one is the best one, okay, by adding up all those different path costs, and the one with the lowest cost wins. So the bottom line is, when any router start building their routing table, they put themselves on this value here, on this X router. Okay, they put themselves on top of the SPF tree, and from there build the branches of the tree, and then they will do the calculation of going to all the possible paths and then add up the cost as we have described. Okay, that's how SPF would work. Any questions so far? Okay. One advantage of link state routing protocol is low bandwidth utilization. It uses very small bandwidth from the link so that all available bandwidth will be used into more important things. It can be used to forward actual data traffic, okay, not just routing information. How does OSPF achieve that? The only changes where when the topology table has been built, after that, if they maintain the table, only the changes will trigger an update going to the neighbors. So essentially, one of the characteristics that we described earlier is, if you go back one slide, actually two, is that they're not sending the full routing table, only changes, only increments. So by doing that, they are able to utilize or have better bandwidth utilization. Only members, basically they're also using multicast, by the way. They send multicast and broadcast, and only the members of the multicast group will receive the updates. So by doing that, it uses less bandwidth. A single packet can be copied onto the members. They don't have to generate individual packets to individual neighbors. It can be replicated and shared with participating networks or participating routers. Okay, so it's a very good characteristic of OSPF. Now, fast convergence. If the primary path goes down, which we have discussed earlier, there is an alternative path, right? And how do we know that? It's all in the topology table. You have there the optimal and suboptimal path. That's how OSPF ensures fast convergence. They quickly run SPF algorithm on the path. Now, if you're finding, I think it's this one, if you're finding, let's say, a new route when a network change happens. So in this case, from router 1 to router 3, the primary path going to router 3 has gone down. So you'll have to find out an alternative path. You notice that there's actually a path via R2. So you hop to R2 before going to your destination. So when a network change happens, as you will see in the steps later on, the router who detects the change will send a trigger through link state advertisement or LSA. When that goes to the neighbor routers, they will identify the changes. If the topology change happens, then again, as I've said, they can quickly run SPF algorithm to find the next best path. And see here, this is your next best path given this. That is done using Dijkstra or SPF technology or algorithm. Yeah, that's one of the examples there. All right, now basic OSPF operations. Let's look at the different stages in the OSPF operation. Those are one, two, three, around four different steps. Okay, let's try and discuss each one. The very first one is neighbor discovery. Okay, so you've set up, you've configured your routers to use OSPF. Now that's done. You've saved up your configuration. Now once you've done that, it will start doing its job. And the first job is to find or discover neighbors. How do they do that? They send hello messages. It's done via layer 3, so they send those L3 hello messages to all the links that are connected. Okay, which links are activated for OSPF? You specify that. So on these links, it will send a multicast message going out to find neighbors. If there's a neighbor in that link, you will know because they will reply via because they receive that via multicast and they will reply to that message. Okay. Now the next one is exchanging topology table. Now maybe you've already found all the neighbors, you've established connections with them. Now you exchange topology table or the LSDB, link state database. So first up is a hello message. When the hello message is received by that neighbor, if the neighbor is listening to that multicast address, they'll be able to reply, right? They'll be able to acknowledge. So that acknowledgement message will be received by your router. And that's the side of it. That's how they build neighbor relationships. This is when, after establishing that relationship, after receiving that acknowledgement, they will then start exchanging the topology table. Okay? They will exchange topology table via L3 multicast. So essentially, actually all control messages are sent via multicast. Next one, using OSPF to select the best path. Now, you already have a copy of the topology table. You already know what's the next step. That's to build hello message parameters, vendor specific or the same. No, you have to look at the RFC. It's a standard. So you check the RFCs that we discussed on the first slide. And you can see there the different types of messages that are sent, and one of them is a hello message. Okay. Next one is using using SPF algorithm to select the best path, which you've already discussed. And then after that, you build up the routing table, and that is now based on the computations that you've done in the previous step. Okay. Now in more detail, so it's kind of a very simplistic way to understand it, but it gives us a good overview of how it works. So we already understand of the different process, but how specifically does neighbor discovery work? So this is a neighbor discovery process. Let's look at this stage in more detail. First of all, let's assume that we have this topology. We have 3 routers connected to this switch. It's a LAN type of network. All of these 3 routers are connected to this central switch. And in terms of OSPF, this is actually what you call as a broadcast multi-access network. Okay. First, of course, you configure the routers to use OSPF. Initially, they are in the down stage or the down state. Now, all 3 routers will then send their address to a packet destination. It's an IP address. For IPv4, it's 224.0.0.5. For IPv6, it's FF02::5. This is a multicast address. Okay, so you will send that to that multicast address. This message will all go to all the routers that are listening to this because they're listening to that multicast address. And this stage is when the routers send their hello message or initialization stage, init state. So So again, you start with down state. That's when you haven't configured it. OSPF is not running yet. Once you've configured, then it will start finding neighbors by sending message to that multicast address. This is what we call as the init state or initialization stage. Next is here, all your neighboring routers with OSPF enabled should have received the hello packet, right? They will then, they don't reply by the way. When can routers struck to init state? As soon as you send the hello messages, that's your init state. Okay. As soon as you start finding or discovering neighbors, it's called the initialization stage. Now, once one router receives that hello message, that hello packet, they will then check the contents of the hello message. They'll have to check what's in there, the information that's there included in the hello message must match my own information. Okay, I'll have to double check with my own configuration. That is the time that they build a two-way relationship or the two-way state. Okay, first of course you have to check the contents if it matches, and that's the two-way state. So what are the contents of your hello packet? These are some of them. Okay, these are some of the required information for establishing connection, or what we normally call as adjacency. Okay, we want to establish adjacencies between us and our OSPF neighbors. Notice the ones with the red asterisks. They are required and must match with the neighbor router to create actual relationship. Okay, they are required. These information are hello and dead interval messages or interval time. The area ID, they have to belong to the same area. Okay, if there is authentication, okay, I also must match that. Should be able to provide that if you set it up in the router that's sending hello message. And that's it. Those are the information that we need to check. Now this is not neighbor relationship just yet. We call it the two-way state, right? Now what happens after that? Next one, after the two-way state, after you've created a two-way relationship between them, that is the time that they will start exchanging network-related information, right? So after basically checking the contents are the same, then that's the time that I will then message back and send my information. At this stage, we have to decide who will send the network information first, because I have a topology database, you have a topology database, we have to exchange them. They must decide which one will start sending first. Okay, we want to avoid collision. If all of them start together, there will be chaos in the network. So they have to decide which one goes first. So which one goes first is the one with the highest router ID. Okay, so it's kind of an implicit understanding among routers. With OSPF, the one with the highest router ID will start the process. This decision process is what we call as the X-start stage. Okay, and then after that, they exchange the actual database, the link state database, and this part is what we call the exchange state. So you notice there are different states that has to be followed. First of all, you have to do initialization, sending hello messages, checking the contents before you can send a two-way state. Once you have done that, you decide which one will send, that's the X-start stage, and then the actual exchange of LSDB is in the exchange state. So a few steps that you have to go through. Now next is when your router already received the LSDB, he has to do a few things. First, it will check what they just received, okay? And also if they already have them, okay? Three possible things can happen here. One is if the router already has the latest and most updated version of the topology database. Again, topology table are shared with everyone and everyone will have the same, right? If it's the same topology or topology table or same network information, there's a field in the database containing the sequence number. If the sequence number is higher or the received sequence number is lower, that means that I already have the most updated version. Okay, so what I'll do is I'll just discard whatever I received, and then it's my turn to forward, okay, my topology table. However, if the sequence number is higher, okay, the one that I received is higher, then that means that the one I received is a newer, okay, more updated version of the topology table. Therefore, I will accept it and the router will override its topology table. Okay, the last possible scenario there is if I don't have the topology table yet. So in that case, I will ask not just this update, but I will ask for the full information. Send us the full information on that particular network update. When that comes, that's how he will now build the topology table. In this case or in this stage, we have established, okay, or we have exchanged the full set of LSDB. This is what we call as the full stage. At the end of the stage, they should have a synchronized topology table. Okay, so I hope that's clear with everybody. Those are the steps followed when you are sending messages. Now, how do you maintain routing information? When you already have your routing table, again, they are sending what we call as hello messages. How often? Every 10 seconds. This is used to make sure that the links are still active. They can also send trigger updates if there are any topology changes in the network. They maintain the link state using the sequence number to make sure that the information are up to date. Also, if there are any link state or advertisements or LSAs, it is usually associated with the sequence number. They always check in their database whether the received LSA has the same sequence number as what they have already in their database. If it's a match, again, discard, get a new one. If the new one is higher, then grab it, override your database. If it's lower, then discard it and then send your own topology database. Okay, so that's essentially how the process works. It simply goes on like that. Every 10 seconds, it will check if the topology tables are still the same, override if not, or send my one if it's lower, something like that. All right, so next one is, by the way, any questions? Sequence number is TCP sequence number. Yes, you can see that. Let's look at the packet contents in a while. I'm pretty sure I have that here. So you'll see what actual values you can have there. Now let's start discussing about the different OS packet type first, okay? By now you know how OSPF works, how it finds the neighbors, how it builds links with them, how it sends and receives link advertisements. Now let's look at the different OSPF packets. OSPF uses 5 packets to essentially do the steps or stages that we discussed in the previous slides. These 5 packet types are used to send control signals or routing information between the neighbor routers. The first OSPF packet type is your hello message, right? You're already familiar with this. Your hello message is sent every 10 seconds. It's used to build adjacencies or links between your neighbors. Another type is the DBD, or the database descriptor packet. This is used for synchronizing the topology database among the neighbor routers. It usually contains the topology information. The next one is your LSR, or link state request packet. Now, if you needed something, requests specific link state of records, then you use it. Why do you use it, or why is it used? If any router has maybe a router forwarding request, but for some reason it's not available on the routing table or the topology table, then the router will ask the neighbors for any information. So do you know how to forward this packet? If a reply comes, then they can build a new routing table again for the packets and the process goes on. But essentially, the link state request is used for that process. If there's specific requests or records that you needed that otherwise is not in your records yet, then you use the link state request packet. The next one is LSU, or link state update. Any reply to the link state request, or LSR, uses LSU, the link state update. If any change happens on the network or any LSR requests come from downstream routers, then the reply will be using the LSU type packet. Okay? And then the last one is LSAC, or the acknowledgement. The link state packet acknowledges all of the above packet types. It's used to acknowledge any link state update or request received. The reason to do so is to ensure their reliability. OSPF uses IP to exchange control information. IP does not have any built-in reliability mechanism. That's why OSPF created a specific packet type to do these reliability, to check for reliability or exchange of data information between them. That's why OSPF have LSAC. Okay, so if you look at the names, they're kind of descriptive in a way, right? You just have to remember the names of these different OSPF types. You're always familiar with the hello and the acknowledgement perhaps, but the other three, please try to remember them and where they are used. Any questions about those types? Okay, so this is the one I was talking about earlier. This is what you have in your OSPF packet. How does your OSPF packet look like? All packets that we saw in the previous slides are included in here. The OSPF participating routers use their IP as a source, the multicast address as a destination. The OSPF packet has the following fields, which we have mostly seen in the previous slides. I'm just trying to see what's important to discuss here, but I have them here anyway. So let's look at each of them. So these are the fields in your OSPF packet. These are the definition of each of them. Version number is, of course, what version of OSPF you're running. Are you using OSPF version 2 for IPv4, or are you using OSPF version 3 for IPv6? The next one is packet type. So let's just go back here so you can see that's a type. It contains either one of the packet types that we have discussed in the previous slide, right? Type 1 up to type 5. So you actually have 1, 2, 3, 4, 5 values contained in the packet type, not their actual names. So you should know which one stands for which. Can I please repeat LSR and LSU? LSR and LSU are basically for requesting and providing link state updates. For LSR, essentially, LSU you use normally. Even if no one asks you, you send link state updates at any intervals if there are any changes in the topology, right? But LSR you normally use to request for specific types of information. The normal times that you would do this is if you receive the packet. Okay, you have your topology database. Maybe you didn't have the updated topology yet, or maybe you just didn't know how to forward that message. Then you request for updates from your neighbors. Ask them how you can send this. Ask them if they have information going to these destinations. So that's typically when you use LSR or link state requests. With link state updates, as I mentioned, you send replies or answers to any link state request is an LSU. Any updates to the topology also uses LSU. Okay, does that answer your question, or do you want me to discuss further? I don't think I have any more to add there, but that's essentially the difference between LSRs and LSU. Okay, so here we were discussing about the type, which is either type 1 to type 5, you'll see there. The packet length is the length of your OSPF packet. Now, these ones important, the router ID and the area ID. What is the router ID? Router IDs defines which router in this is the source of the packet. Okay. Typically, when you configure something, you use the IPv4 address in the router ID. That's not always the case, but common practice is to use that as your router ID. Okay. As I've said earlier, a router ID also plays some role in defining which of the router will go and send the updates first. If you have a higher router ID, then you go first. Now, next one is area ID, which defines a particular area where you can only send or exchange topology information with those that are in the same area. Remember that in the slide that covers the contents of your hello message, it has there, and it's required, you have there the the area ID. And it's important that it matches with the area ID of the one that sends the hello message. All right. Next one is checksum. It's used for any error detection to ensure that your OSPF packet is not corrupted or you need to do transmission. And last is your authentication type, which is done if you're adding any authentication. The actual data, the actual information is contained here, and the value or the contents of your data field depends on the type of packet or type of OSPF packet. Okay, so these are the contents of your OSPF data packet. If it's hello packet, then it should contain a list of all the neighbors. If it's for DBD, it contains a summary of the link state database. If it's a link state request, it contains what LSU you needed. Okay, if it's a particular LSU, also included is your router ID that needed the LSU. If it's an LSU packet, it contains link state updates or link state acknowledgements and any answer to an LSU request. And if it's an acknowledgement or LSAC, the data field is usually just empty. There's no contents in it. Okay, so again, the contents of your OSPF data packet will vary depending on the OSPF packet type. Any questions? All right. Now, I usually get questions about differences between OSPF v2 and OSPF v3. OSPF v3 is not an update to OSPF v2. It's not like I have OSPF v3, I don't need OSPF version 2 anymore. Only, you actually do. OSPF v3 is only used for IPv6. But when you look at the packets, okay, you notice that there really isn't much difference between v2 and v3. What changed there? Now the router ID is still 32 bits. So typically, okay, when you configure a dual stack router with OSPF, what you normally end up doing is to still use the IPv4 address of your router. Okay, this poses a bit of a problem when you use only IPv6. Okay, obviously your router ID is just it's just a number. It can change, but since we have some dependencies on IPv4, then sometimes it can be confusing. So that's one of the main things. Again, the router ID is still 32 bits in OSPF v3 for IPv6. So operations wise, the v2 and v3 are kind of still very similar. Okay, obviously the source destination addresses will change from 32 bits to 128 bits. Okay, but other than that, most of the contents of the packets are pretty similar. Any questions so far? So we've looked at the OSPF structure from a packet level. You've looked at the different packet types, the fields into the OSPF packet. Now the last one is about network topologies. So if you're building OSPF networks, it can be built using different topologies. We have three. I have that in here. Yep. You have broadcast multi-access, point-to-point networks. It can be Ethernet, it can be using X25 frame relays. So depending on your topology, the way OSPF works to build neighbor relationships may vary, may be different. So it's necessary to understand the topology when building your OSPF network. So topology usually falls under these three types: broadcast multi-access, or um, BMA. You have point-to-point, and you also have non-broadcast multi-access networks. The typical one that we have discussed all throughout is broadcast multi-access. So generally, LAN-type networks such as Ethernet or even token ring are using this type of topology. Neighbor relationships are created automatically, so it's quite easy. When all the OSPF routers exchange information, the problem arises here is that, okay, can I repeat slide 24? Sorry, which one, slide 24? Ah, here. Okay, we're just about starting network topology. So, okay, let me just discuss that very quickly again. What we've discussed before this are OSPF from a packet level, right? So different packet types. So here, what we want to discuss is the different OSPF topologies, because when you discuss or describe how your OSPF functions in different types of topologies, there are differences. Okay, if you build an OSPF network, it can be built on different network topologies. Can be point-to-point networks, can be using WAN, can be using serial interfaces, can be using Ethernet, can use X25 frame relays, and so on. So it's necessary to understand the different topologies. And just quickly go through here that there are three typical types of OSPF topology: broadcast multi-access, point-to-point, and non-broadcast multi-access. Broadcast multi-access is LAN type of network. They will share the same Ethernet links. Point-to-point networks are usually just two routers that are connected via serial interfaces. And the last one is non-broadcast multi-access, which normally is connected via the one service provider. So they provide either usually X25 frame relays or ATMs. Okay, broadcast is usually not allowed in this type of link. So now on a layer 2 level, how do you think will the multicast frame be forwarded? So you have to understand how that will work. But before we go to that detail, let's discuss about broadcast multi-access. Broadcast multi-access is your general LAN type of technology. Okay, when all the problem that arises here is when all the OSPF routers exchange information. So there is a possibility that you're wasting bandwidth. So to have some form of discipline, a typical thing that happens in broadcast multi-access is you will have different roles. You will elect a DR, or a designated router. You will also elect, or they will also elect, a backup designated router. The designated router, okay, is the one with, I think, the highest. Let me verify that. Yep, the I lost something. Basically the DR, or the designated router, will act as sort of the leader of the OSPF link. All of the other routers, they will send updates, but they only send updates not to everyone, but only to the DR. It is now the DR's responsibility to forward it to all the other routers in the link or in the network. So he's like a central OSPF speaker. If DR is down for some reason, the backup DR will step up and will act as the leader of the pack. It will act the role. So to summarize, in a broadcast multi-access, you'll have a DR. It will be elected, followed by a BDR. Then they all send messages to the DR. Then the DR will send the messages going, or forward the messages going to all the others. How do they do that? They again using multicast addresses. packets are sent to the DR and BDR via 224.0.0.6 IPv4 address or FFO2::6 if it's an IPv6 address. And then from the DR, it will be forwarded to all the other routers via another multicast link. Now we're using .5 and ::5 rather than 6. Okay. Now all neighbor routers form full adjacencies with the DR and the BDR only. They don't have to have full adjacencies going to all the other routers in the network. Okay. Now, how do we go about the DR and BDR election process? So, which one will act as the designated router? The router with the highest priority value is a DR. The router with the second highest priority value is the BDR. Remember, there's a priority field in your OSPF packet. In the event that both of them have the same PR or priority value, sorry, then they will look at the IP address. Okay, the one with the highest IP address on the interface that is using OSPF will become the DR, and the second highest will become the BDR. However, if you want to select a particular router to become the designated router, you can also do so. You have to then edit or manipulate the router ID. Okay, so one with a higher router ID, because you know router ID usually we use the IP address, right? So you change the router ID so it is higher, so it will become the designated router automatically. Okay, simply change the priority or assign a higher router ID if you want a particular router to become the DR or VDR. Okay, any questions in this? This is a typical OSPF setup, OSPF topology that we use, so it's kind of easy. Next one is point-to-point networks. The second topology is when your routers are connected back-to-back using a serial link. Usually we use L2 technologies, L2 encapsulation methods here, use PPP, HDLC. This one is pretty straightforward. There's no need for a DR or BDR because obviously you only have two routers, right? They build neighbor relationships, which is your full OSPF neighbor relationships by exchanging messages with each other. They still exchange hello messages every 10 seconds. And then dead intervals is around 40 seconds. Okay? So that's point to point. Again, it's just pretty straightforward. The next one is your, by the way, do you understand it when I say hello and dead intervals? So typical values are 10 and 40, but and dead intervals are usually 3 times as much as your hello interval. A hello interval are when the packets sent to OSPF neighbors to maintain connectivity, right, which is like 10 seconds for Ethernet. It's actually more if you talk about non-broadcast links, as you will see later on. Dead intervals, on the other hand, is hello packets include a list of all the neighbors for which a hello packet has been received. So it has to be within the dead interval. If the router does not receive a hello packet from a neighbor within that dead interval, it will now declare that neighbor as down. So I think someone asked this early on as we were just about starting. So this is the answer to your question. It stops becoming part of your neighbor if you don't respond within the dead interval times. All right, and that value is 40 seconds for, yes, you can change the intervals. Typically you only do that for broadcast multi-access, but for others, I think you can still change it, but not typically done so. Okay, but these are the typical values. 10 seconds for hello, dead intervals is 40 seconds. Now, the next one is non-broadcast multi-access, which is more exciting. As I've said, this includes things like, say, WAN technologies, frame relays, ATMs, X25. What does it mean exactly to be non-broadcast? So if you look at this diagram, we have one service provider diagram, right? If you need to send packet from one side to another side, it will be forwarded using virtual circuits. And you know how virtual circuits work. It's one way. If you need to send packets back to the source, to the other end, the other side, it should use another virtual circuit. Now, when the OSPF sends OSPF packets, there is no way for it to be forwarded to the other routers. Okay? It can only be sent once in the virtual circuit. It can't be forwarded anywhere else. Okay? So that's kind of an issue. So how do you discover DRs and BDRs? It cannot be discovered automatically in this type of setup. But you have an option to do it manually. So they both have to be built manually. All neighbor relationships must also be built manually, and that's because you don't have any way to do it otherwise, right? So how do you do it? You need to manually configure your routers to have these neighbors using neighbor relationship statements on both sides and all that. That's the only time that they can start exchanging hello messages with each other. All right. So in the NBMA network, the default hello interval, as you see, is much larger. It's 30 seconds hello, and the dead interval, as I've said, is usually three or four times. Sorry, it's four times. So it's 120 seconds for an NBMA. All right. Any other questions? I think I've answered all of your questions there. Are there any other questions with the different types of topologies? If not, that's where this class ends. It's a good in-depth overview of what OSPF is, how it functions, uh, how do you establish connections, relationships, adjacencies with other routers, and how do you typically set up the topology database. So I hope you got something out of this. If you want more clarifications, if you have more questions, please write them down in the chat. Meanwhile, I'm going to write down the link to the survey. So if you can please answer this survey for me, that will be really good. Okay, so this is the link to the survey. Please spare some time to do this. If you want a copy of the slides, you can download that from FTP. The link is this one. I normally link that to the survey, but it feels like it's not redirecting straight away. So that's the link to the FTP if you want a copy of the slides. Also, that's the last session that we have for today. Thank you very much, everyone, for joining in. I hope that you learned something, and I hope that you will be able to learn more on different routing protocols. We have other more advanced courses on this, so please check out training.apnet.net/events for all the upcoming sessions. All right, again, thank you very much, and I hope to see you again another time. Bye-bye.